Welcome to the first geometry video on this channel. The topic we're going to be covering today is a very important one, and I cannot stress that enough. If you don't know this topic in geometry, it's going to be pretty hard to get good at it. So let's learn about it. Today we're going to be talking about triangles which share an altitude or a base and what that means for the ratio of their areas. This is a very important relationship in geometry. It comes up over and over again, so you want to know it. You want to have it in your geometry toolkit. A couple of things we need to get out of the way before we start though. There are a few prerequisites before this, so if you don't know much about similar triangles, the fact that the area of a triangle is equal to half times base times height, and if you don't have some general knowledge on the Pythagorean theorem, it could be a little harder to follow with this video, so you might want to check my videos on these three first. With that out of the way, I think the best way to introduce this new topic is with a warm-up exercise. So let's get straight into it. So over here you can see we have a triangle, and we need to find a few things. As you can see to the side, first we need to find the ratio of the area of triangle ABC to the area of triangle ACD. So let's get that notation out of the way. So from now on, whenever you see this thing in square brackets, this just means area of triangle ABC. So that's what that means. So then this means the area of triangle ACD, and this means the area of triangle ABD. Right, and you can see those triangles are all here. So this is triangle ABC, this is triangle ACD, and this is triangle ABD, this big one right over here. So let's answer these two questions and see if we find anything interesting. So the light bulb over here is going ding, 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 because this is just something I want you to remember whenever you see problems like these. It says to drop altitudes, keyword being altitudes, and to use variables. And I said keyword is altitudes. We love altitudes because, in general, in geometry, we always like 90 degrees, and altitudes are the best way to introduce 90 degrees into a problem. So to answer our first question, what I'm going to do is I'm going to take this triangle and paste it over here. Now the thing with this triangle is, I'm going to show you, I see there are two triangles within this bigger triangle. There's triangle ABC and triangle ACD. So I think what we're going to do is we're going to split them and look at them individually. So leaving this left side, we only have triangle ACD, and then I'm going to go ahead and erase the left side again over here and leave us with triangle ABC. So the erasing might not be perfect, but I'd say that's good enough for now. So let's use our tip. It says to drop an altitude. Okay, where can we drop an altitude? How can we do this? How does this look to you? Let's drop something from A. Remember, altitude means you go straight down and this would be 90 degrees. So that's what we call an altitude. Now for this bigger triangle, triangle ABC, we're going to drop an altitude from point A. And I want you to remember that this handy little tip over here tells us that altitudes of obtuse triangles lie outside the triangle. And that's because we're just going to have to extend side BC so that the altitude can actually meet it over here. If any of this does not sound familiar to you, this is what I'm talking about for the prerequisites, so I would definitely check those videos out first, because I'm not going to explain in too much detail in this video why the altitude of an obtuse triangle is outside the triangle. This is something you should already know. Now we can't forget the second part of our handy little hint over here. It says to use variables. So let's go ahead and call this height h. H for height. Now, what about this height over here? Should we go ahead and call it a different letter like M or N? Well, we could, but I think a better letter to use is actually the same letter itself, H. Sorry, that was not the pencil, that was the highlighter. Okay, here. There we go. So I'm actually using the same letter for both of these heights. Now, why can I do that? Well, that's because both of these altitudes are dropping from the same point, point A, right? That hasn't changed, and this one drops to CD, and this altitude drops to BC. And if we take a look at our original triangle, so if both altitudes are dropping from point A, the thing is they're dropping to CD and BC. But the thing is, B, C, and D, they all lie on the same line. So we really have the same altitude for both triangles. That's why I can call both of them H. Let's take some areas now. The area of triangle ACD, since this is a triangle, we have a base and a height. Therefore, we have this useful formula, half times the base, 20, times the height, h. That simplifies to 10h. Let's do this one. The area of triangle ABC is half times the base, 30, times the height, h. 15h. So if we are to go ahead and answer our original problem, we just need to take the ratio of these two areas. So the ratio of triangle ABC to the area of triangle ACD is 15h over 10h. This can be simplified after some cancellation and simplification. So I'm just going to get rid of h's, and 15 over 10 simplifies to 3 over 2. So the final answer is 3 over 2. Now, the number 3 over 2 is very, very interesting because maybe some of you keen-eyed people might have already seen that it's actually the same as 30 over 20, which is the same as the numbers given in the problem. 30 is segment BC and 20 is segment CD. So when we combine everything together, actually what we have is the ratio of triangle ABC to the area of triangle ACD is equal to BC over CD. There we go. So this is just something I want us to remember. Let's call that number 1, because we still have another question to answer. So I'm going to paste the same triangle over here. This time we need to find the ratio of triangle ABC to the area of triangle ABD. The great thing about triangle ABC is we actually already know what it is. It's actually already found. We found in the first part it's equal to 15H. So all we need to do is find the area of triangle ABD. So let's do that. You know what to do. Drop an altitude. And the great thing about this app actually is that if we want, of course it's still there, but if we want, we can sort of imagine like this is not here. This segment AC, if it's a little distracting for you, because you just want to focus on this big triangle, well, we can get rid of it. Again, this height still is length H. And now we can actually calculate what this area is. The area of triangle ABD is equal to half. Don't know what happened there. It's equal to half times the base. Base BD is BC plus CD, which is the whole segment BD. That would be 30 plus 20, 50. Half times 50 times the height H. Simplifies to 25H. So if we take the ratio that we're trying to find, we already found in the previous part, this is 15H. We just found that this is 25H. After some simplifying, this ends up being 3 over 5, which is the same as 30 over 50, which is the same as BC over BD. So I can write that out more clearly over here. BC over BD. Great. Let's just go ahead and call this number 2. So after these two examples, we found that the ratio of the area of triangle ABC to the area of triangle ACD is BC over CD. And we also found that the ratio of the area of triangle ABC to the area of triangle ABD is BC over BD. This is very, very exciting for me. I don't know about you. Perhaps you don't see it yet, but it'll all be clear on the next page because what we found is very, very important. So let's go to the next page. This is our very useful result. It says if two triangles share an altitude, then the ratio of their areas is the ratio of the bases to which that altitude is drawn. And you can go ahead and verify this in the previous examples that we did, but I have another example right over here. If you don't know what I'm talking about, this will make it very clear. And I want you to remember that this useful result that we just found is particularly useful for problems in which two triangles have bases, keyword being along the same line. Alright, so I'm back with the actual problems because for some reason they just disappeared, but basically this is what we're trying to find. Okay, so you can see triangle ABC and triangle ACD both share the same altitude coming down from point A, and then our result says the ratio of their areas, this, is the ratio of the bases to which that altitude is drawn. So in triangle ABC, the altitude from point A is being drawn to base BC, which is 40. And then in triangle ACD, that altitude is being drawn towards side CD, which is 30. So very quickly we can answer that this is equal to 4/3. We can do the same for this next problem. So we can see we have two triangles, triangle ACD and triangle ABD. They both share an altitude coming from point A down to this side. So in triangle ACD, that altitude is being drawn towards side CD, which is 30. And in the big triangle ABD, it's being drawn towards BD. BD is equal to 40 and 30. That's 70. So this is equal to 3/7. And so you can see in the end, we can almost sort of informally, I guess you could say, think of it like this. Since both of these triangles share an altitude from point A, we can almost cancel these A's, although that's not what's really going on, but this is, again, an informal way to think about it. Basically, it's almost like these A's are like going away, and then what we're left with is BC, so we just read that off. BC is 40, CD, just read that off, that is equal to 30, and voila, we get those over here. So we're not really canceling, but we can technically think of it as canceling because of them both sharing an altitude from point A. So that quote-unquote canceling is coming from over here, the fact that they both share the same height h. So that's why it goes. So again, here, since they both share a height from point A, we can almost cancel these A's and then read off what we're left with. So CD is 30, BD is 70. This is just a little fast way that I sort of think about it as well, but again, understand where it comes from. It's because of the same height from the same point. So besides triangles sharing altitudes, triangles can also share a base as well. So this is just another case. It's very similar to the first result that we just found. And it says if two triangles share a base, then the ratio of their areas is the ratio of the altitudes to that base. So over here, that's a mouthful, but let's break it down. You can see we have two triangles, BCD and B, that was horrible, BAD. And they both share a base here, right? BD, which I've gone ahead and labeled B. So the height of triangle BCD is 8, and the height of triangle BAD is 13. So if we wanted to very quickly, again, this question sort of disappeared, so I'm going to have to fill it in again. If we want to find the ratio of these two triangles, and you know what, let's be consistent actually, because if I go like this, I want to go like this as well. So this ends up being, in triangle BCD, we have half times the base, which is b, times the height is 8. And then in triangle BAD, half times the same base. They share a base, remember, but the height's a little bit bigger. So we get a ton of stuff goes away, and we're left with 8 over 13. Which is the exact same as these numbers over here, which we can just read. Again, because they share a base, this cancellation takes effect. So we've gone over triangles that share an altitude and triangles which share base, but I can tell you right now, all the problems that we're going to be seeing later. Yes, we do have practice problems coming up, so that's the fun stuff. But anyways, all of those practice problems will mainly be focused on triangles which share an altitude, because those require a little more insight, a little bit of tilting your head, and just shifting your perspective to see the shared altitudes. And so they just have more applications, and they're just more fun to work with in general. So that's what we're mainly going to be concerned with. So let me write that down for you, my students. We will mainly be concerned with shared altitudes. As opposed to shared bases. Because in general, this stuff is more fun, just has more applications. So let's take a look at our first problem, which is going to use this result. And I'm going to get this out of the way right now before we begin. All problems tonight can be solved with just this one result that we just found, and some of the prerequisite stuff, but it's mainly this thing, okay? So it's one thing to know it, it's another to use it, because you might be looking at those problems and saying like, you know, I don't really see how I can just use this concept to solve it, but I assure you, you can. It's all just a matter of practice and how you change your perspective. So, how well you can see things. Yes. So, this is the more important part. Let's get to the actual problem. So this is your first problem. As always, I encourage you to pause it and try it out on your own and see what you can do. So here's the problem. We have this shape over here. The area of triangle ABX is equal to 24. The area of triangle BCX is 18. The area of triangle CDX is 15, and we need to find this last area. The area of triangle ADX, marked with a question mark. So this is a very typical problem which uses the same altitude concept. you're basically given a bunch of areas. So we're given these three, and we need to somehow relate them to each other to find this last unknown area. As I said before, it may be tricky to apply what we just learned, but that's why we need to get a lot of practice. We need to see the altitudes. That's my hint to you. You need to see the altitudes because right now they're not there. So you need to add them. And that's what the essence of geometry basically is. Train your eye. You need to train your eye to see things that are not there. Sometimes you might need to train your eye to remove things that are there. Sometimes you need to train your eye to extend existing things. But anyways, that's besides the point. Today, it's all about seeing the altitudes that are not there. If you don't know what I'm talking about, let's get into it. What altitudes am I talking about? And actually, right away, I can tell we're going to need another page. So I'm just going to do that very quickly. Okay. Now, I've just gone ahead and pasted the problem so that we can focus on a specific section of this diagram. Now, as I said before, training your eye is basically the essence of geometry, which is why, in my mind's eye at least, when I see this first problem, I immediately see two shapes. I see two triangles. And I just drew them right over there. So there's this triangle, triangle ABC, on the right side of the diagram, and this triangle, triangle ACD, on the left side. Let's focus on the right side first. And as I said, since I have an app, I can do this. Very useful. It's very useful. We can just get rid of it. So this should hopefully help you see what's going on more clearly. Hopefully that's good enough. The next thing I want us to do is to introduce an altitude. So right now there is no altitude. We need to bring it. So where can we drop an altitude from? There's not really many options. The best is from here. This is the best choice. From point B. And I'm going to do a little bit of maneuvering once more because let's just turn this. In general, for a lot of people, it's easier if they see an altitude like this as opposed to before when it was on an angle. Now I can actually adjust these letters very quickly. I believe this was A, B, C, and X. And now I hope you see within this triangle, we actually have two more triangles. We have triangle BCX, and we also have triangle ABX. If you haven't noticed, I like going in alphabetical order. So these two triangles actually triangles ABX and triangles CBX share an altitude from point B. And I know I said I like to go in alphabetical order, but actually I changed my mind. There's a very specific reason why I'm writing it in this order, and I think you'll see later what I'm talking about. So make sure you see that. If you want, we can go even slower. So BCX, this is our altitude. In ABX, as before, since it's an obtuse triangle, we need to extend this side, and then the altitude meets here. This means, from our very useful result, we actually can find that the ratio of the area for these two triangles is equal to AX over CX. Again, with the informal quote-unquote canceling strategy, and this is why I wrote it in this order, the B's line up, so take away the B, you're left with AX. Take away the B here, you're left with CX. And now we can read off of our diagram. The area of triangle ABX is given to be 24. CBX is 18. This means AX over CX is equal to 4 over 3. This is very, very useful. I'm going to save this for later because we're going to come back to it. It's so important, we're going to label it number 1. Now, same thing. Just going to make the diagram a little bit bigger actually. Now we'll focus on, as I said before, we're going to focus on this triangle. Let's go ahead and erase this. So this goes away. Our next step, drop in altitude. So you can see it's pretty much the same process, just repeated many, many times. There are many choices on where we can drop in altitude, but I like the looks of this one. If you're having a hard time seeing that, let's tilt it so that it's easier for you to see. I'm going to fix these letters real quick. A, D, C. Let's just fix that. Okay. And why not? Let's fix this as well. It's a little ugly. So this is X. Okay, this time, I hope you see two triangles within this triangle. I hope you see triangle ADX, and I hope you see triangle CDX. I also hope you see that they both share this altitude. So triangles ADX and CDX both share an altitude from point D so then this means that the ratio of their two areas is equal to, this is the unknown area that we're trying to find. The area of triangle CDX is given to be 15. And then we can almost pretend, again informally, as if we were chopping these away. We're left with AX over CX. Okay. So we have the area of triangle ADX over 15 is equal to AX over CX. I wish I knew what AX over CX was, because that would be really helpful. Oh wait, we do. If we look back over here, we know this should be equal to 4 over 3. If we put everything together, now what this means is that we have this very simple equation which we can easily solve. I'm not going to go over how to solve this in too much detail because I'm assuming that you already know how to. you should get a final answer of 20. And because we don't have units, we're just going to leave it as a number. So, a couple things to go over. I think we can all agree that solving this is not the hard part, and it's not the most important step. The important part is seeing these triangles which share an altitude, and setting up these equations. Because once you do this, everything else just follows. So that's what we're going to be focusing on. We're going to be focusing on seeing the altitudes and setting the equations up. So I'm not going to be going over in too much detail how to finish the problem by solving. Okay, that was question number 1. I hope you see how that was solved. I also hope that this, what we did over here, when we like chopped off one side and, sort of rotated everything around, I hope that sort of helps you see better. Because let's get into question number 2. So here's another type of problem that you're going to see. This one there's a bit more going on because now we have side lengths and their relations to each other. So we're given CX. This thing is twice as long as BX. That seems legit. That looks about right. We're given AY is about 3 times as long as BY. That also seems correct, but as usual, you should never assume your diagrams are drawn to scale. But in this case, I guess it looks like it. Anyways, that's not the point. We're given that the total area of this big triangle ABC, is 120, and we need to find the area of triangle BXY. So this little guy over here. So without wasting any time, let's get into it. So I'm going to start off by calling BX length A. Let's just call BX equal to A because then we can write CX as 2A because it's twice as long. Let's call BY B, so AY is 3B because it's 3 times as long. Let's also call this little area that we're trying to find, let's give it a name. Let's give it S. Why not? S for small. Okay, first things first. I hope you can see that within this big triangle, we have a couple of other triangles. So this is a very important thing to do. This is how you're going to get better at geometry. Just keep seeing the triangles within the triangle, within the bigger triangle. Smaller triangles within the bigger triangle. Okay, that was a mouthful. So I see we got one here, and we got the tiny one here, and we also even have actually this one, and we even have this one. So wow, there's quite a bit, but let's focus on these two first because that has what we're mainly concerned with. We're mainly concerned with triangle BXY. So if we can write everything in terms of S, so this is the goal. The strategy is to write, so let's write that down actually. I didn't exactly plan this, but maybe it's a good idea to do so. So here's the general strategy. Let's rewrite all areas in terms of S and then use the fact that the total area is 120. This is our game plan. It's very important to have a strategy before you dive into a problem. So I wrote this in terms of s. If I can write this in terms of s, and then I write this in terms of s, well then we've got the whole area of the entire triangle, and we can set that equal to 120. Let's do it. Again, I have the luxury of an app, so I get to copy stuff, I get to erase stuff, I get to move stuff around. Okay, so I've just gone ahead and erased the entire left side because we won't be needing that. And again, to help you visualize things, I will be moving this around a bit because it's time to drop an altitude from point X. Right over here, straight down, and then let's rewrite everything just so that it's a little bit more aligned. I believe this was correct. Okay, and why not? Let's orient this the right way as well. Okay, triangles BXY and AXY. That was a horrible AXY. AXY and BXY both share an altitude coming down from point X. Triangle BXY and AXY both share an altitude from point X. This means we can find the relationship between these two areas. This ends up being, if we pretend the X isn't even there, AY over BY. AY ends up being 3B, that's what we called it. BY is B. B's cancel, leaves us with 3. So now we've actually found a relationship between the area of triangle AXY and BXY. We know the area of triangle AXY is 3 times larger than the area of triangle BXY. The area of triangle BXY is S. Sorry, it's kind of tilted, but okay, over here. You see it's S, which means the area of triangle AXY is 3S. Awesome. We can go ahead and fill that into this diagram. 3S. That's very, very useful, what we just found. Let's continue our success. Same thing. Now, I'm actually going to fill this in with 3S. Because now, this is actually oriented the right way. Actually, I was going to turn it around, but no need to. I'm going to drop an altitude from point A. And guess what? We have two triangles, triangle ACX and triangle ABX. They both share an altitude coming down from point A. So triangle ACX and ABX share an altitude from point A. Again, I hope you see that this is basically just the same thing applied many, many times. Sometimes we're just changing our perspective on how we view things. So first we were viewing from these two triangles, and now we're viewing with these two triangles. Anyways, this means that they are related like this. The ratio between the two, if we pretend the A isn't even there, because remember it's coming from A, we're left with CX to A, BX is A. So it's 2. This means the area of triangle ACX is twice as large as the triangle, or the area of triangle ABX. And notice the area of triangle ABX is equal to the area of triangle AXY plus BXY. You can see here ABX is just 3S plus S. So we're going to continue that. So that's 3S plus S, which is 8S. I'm going to go ahead and add that back to the original diagram, because now we can finish the problem. So if we go back to our strategy, we managed to successfully write everything in terms of S. This means we can use our final information in the problem. So remember, always a good tip, use what you haven't already used yet. So we've used this, we've written everything in terms of S. Now we just need to finish with this last piece of information. The total area of triangle ABC is 120. So let's do that. If the total area is 120, that should be in black. So this is how I would write my solution, since the total area is 120. This means we need to add up all 3 areas and set them equal to 120. You can solve this and see that S ends up being 10. So this means the area of triangle BXY is 10. I'm going to fix that actually. Don't really like that. There we go. Much neater. Let's move on to question 3. Okay, here's question 3. Now question 3 actually has 2 solutions that I'm going to present. Because it's always nice to see multiple solutions, and you're not necessarily wrong if you solved it in a certain way. I guess it just shows what type of problem solver you are. Keep in mind, one is not better than the other. They're totally valid. And anyways, this question, almost, at least in my mind, I sort of see it as a sort of fusion between the 2 previous problems we did. So if we were able to do those, then we should be fine here as well. Because as you can see, the setup is sort of similar to 1. Right? We got these 4 triangles here. Only this time we're given 2 areas instead of 3. We still need to find the area of 1 triangle. And this is where, the part from question 2 comes in. We're given the total area. Only this time it's not really the total area of a triangle. It's the total area of a quadrilateral. It is equal to 60. We need to find this area here, the area of triangle ADX. So let's get started with solution 1. So I'm going to go ahead and let's bring this down. Gonna get rid of that. Okay. So I hope by now we're getting used to it. So in my mind, just like problem 1, I see 2 big triangles. And of course, within these big triangles, there are these smaller triangles. And the fact that the left, if we were to break up the triangle like this, the fact that we have AX and CX, and if we were to divide it like this, the fact that we have AX and CX again just sort of tells me we're going on the right track. Maybe we can set things equal to each other and go from there. So I'm going to erase this side first. This is an X. Same thing, repeated over and over again. Repetition, repetition. Drop an altitude. I won't do this every problem, but I think this will be the last time that I actually tilt it for you, because by this point I think you can understand it. I just do this to make things very clear for you. But eventually we will have to graduate from these baby steps of tilting every time. As you get better, it should be much easier for you to see this in your head. So notice triangles ABX and CBX share an altitude from point B. When in doubt, always just draw the triangles out. So here's CBX, that's the altitude, and ABX, an obtuse triangle, so the altitude is outside. This means we can find a relationship between their areas as follows. We can almost pretend like the B's are not even there. And we're left with AX and CX. The area of triangle ABX is 6. CBX is 12. This simplifies to 1 over 2. So I'd say this is a very useful thing to keep in mind. Let's just write it as a little aside. AX over CX is equal to 1 over 2. Just something to keep in the back of our mind. It's time to do some more pasting. And this time, we already used this side, so we're going to get rid of it. Now, to make things easier, so that we don't always have to refer to it as the area of triangle ADX. Let's just go ahead and call this M. Let's call this N. Next step, draw an altitude. The altitude is coming from point D, and it's going straight down. I will take this triangle and tilt it, so that's easier for you to see. We're going to go ahead and relabel this. And I think I'm going to go ahead and actually write this out like this. I hope you see the two triangles which share an altitude. Triangles ADX and CDX. Share an altitude from point D. So then this means that their ratios, let's pretend like that D isn't even there. And like magic, we get AX over CX. This is good news because, and you can always do this in the middle of your solution, if you can see that you're going to line things up nicely, you're on the right track, so keep it up. The area of triangle ADX is what we have called M, and the area of CDX is N. So we actually have this. So if we know that AX over CX is M over N, but we also know that the area, or AX over CX is 1 over 2, well, guess what? We can set them equal to each other. This means 1 over 2 equals M over N. So N is equal to 2M. If we just cross multiply that, and now from here we might seem stuck because we have two variables, one equation, but this is why you always need to go back and use everything you're given in the problem. We are given that the area of ABCD is 60. So if I go ahead, so we called this M and this N. So since the total area is 60, that means M plus N plus 12 plus 6 is equal to 60. And now we have another equation. We also know that M plus N plus 12 plus 6 equals 60. M plus N must be equal to 42. And again, I'm trusting that you can solve this on your own. The important part is how to get here after all. And what you're going to find is that M ends up being 14. Because we are trying to find M, aren't we? Because ABX, yes, ADX, that's my bad. Got the wrong letter. ADX is equal to 14. That looks about right. Okay, so this was the first solution, and to be honest, this is actually what I think immediately, but maybe you are built different and you're more like the second type of problem solver. Keep in mind, it's still going to be the same concepts, just applied a little bit differently maybe. So maybe you're more like this person. So now let's get on to solution 2. I'm going to take this one and paste it. So maybe you're more like this. Maybe you see the triangle ABX, and this time instead of CBX, maybe you see this big triangle ABC. So maybe you saw this instead, because they still both share an altitude from point B so this means that the ratio of these two areas, if we pretend the B isn't even there, we actually get this time AX over AC. The area of triangle ABX is 6, and the area of triangle ABC is 6 plus 12, which is 6 over 18. That's the same as 1 over 3. So as a little aside, let's write that. AX over AC is 1 over 3. Cool. Let's just box for consistency. Don't know why that was so square. That's like such a square box. But anyways, just something to remember. And then what we can do is we can actually take this one as well, because it's more or less the same thing. Over here, and this time maybe you saw that triangles ADX and triangle ADC share an altitude from D. Again, focusing on that bigger triangle ADC. This means that the ratio of these two areas, pretend that D isn't even there, AX over AC, the area of triangle ADX is equal to M, and the area of triangle ADC is equal to M plus N. Now the thing about M plus N, let's just write it as a little aside. So we might not know what M and N are individually, but if we go back to our problem that says the total area of ABCD is 60, M plus N plus 18 equals 60, which means M plus N is 60, take away 18, which is 42. 60 take away 18 is 42. Sorry for writing the 2's differently. I don't know why I do that. Anyways, from here, we get that AX over AC is equal to M over 42. AX over AC is equal to 1 over 3. AX over AC is equal to M over 42. Therefore, we set them equal to each other. M is equal to 14 as before. So since we got the same answer 2 different ways, we can be pretty confident that we are correct. So, as I said before, I'm more of a solution 1 type of person. It could be seen as less efficient because you're finding both m and n, which might seem unnecessary. But in solution 2, it's a little bit quicker. You find m just a little bit quicker. So, slightly more time efficient. But both are completely okay. So I hope you're seeing how these altitudes play a very important role to solving these problems, because what's coming next is pretty crazy. So good luck with question 4. Feel free to pause the video because this one is not as straightforward. I would say this is where things definitely get a little bit harder. Question number 4 says, a farmer owns a triangular field as shown in this diagram. So this is the field. He knows 5 sheep can graze in the west field, 10 sheep can graze in the south field, and 8 can graze in the east field. And the big question is, how many sheep can graze in the north field? So this little section over here. Given that all sheep eat the same amount of grass. So I think it's very clear that this question can be turned to something like this. So I'm just going to enlarge the diagram, and let's get rid of these letters and fill them in with our numbers. So west is over here. That's 5, 8, and 10. I'm also going to go ahead and let's put some labels, because if we have triangles, we want to refer to them by letters. So let's say triangle ABC. Let's call this D. Let's call this E. And let's call this section F. So if we look at our little buddy over here, it says to add a line in this problem, because that's going to help us a lot. So that's the thing about geometry. In geometry, sometimes you're going to have to add a line that isn't there. And the million-dollar question is always, which line do you add? Because some choices are going to be better than others. Now, as for finding out what this line is, you can only do that through lots of practice. But at some point, you're going to get really good, and you can see that I personally think adding this line is going to help a lot. If we connect C to F. So why would I do this? Well, a good place to start is because this north region isn't exactly a triangle right now. As you can see, it's this funky quadrilateral, so we can split it into 2 triangles. And I hope you can see, over here we have triangle CDF, and over here we have triangle CEF. And the reason that I chose this line instead of this line, some of you might have been asked, some of you might have been wondering why we didn't draw the line like this. And that just comes down to the notion of symmetry. So I want you to just keep this in the back of your mind. A lot of times for problems, it's a good idea to keep things symmetrical. So we can see there's a line coming from A that goes to F. There's a line that comes from B that goes to F. So it would be pretty nice if there was a line coming from C to F. And now we have a few triangles. We got one here, another here, 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 and here. And since this north region has just been split into two, let's say it splits into areas of X and Y. So the goal is to find X plus Y. Because these two combined areas is the entire north region. So great, we have a strategy now. Let's do it. And we're going to be using the same altitude principle that we've been doing this entire time. So I'm just going to move this actually over here so I can cleanly grab this diagram, and let's get to work. So I've just gone ahead and done some work on this. I've erased that a few things, and I've left us with these two triangles because these are the ones I want to focus on. So now that we're getting better, I'm not going to always rotate things around like I did before, because by this point I think we're getting very used to it. So we have two triangles, CFD and AFD, and I hope you can see that they both share an altitude coming from point F. So since I'm not rotating things anymore, you might have to tilt your head a bit, but at some point, as you get more practice, you're going to see the altitude very easily. This means we can get a couple of things. So the ratio of the area of these two triangles is CD over AD. The area of triangle CFD is called X. The area of triangle AFD is 5. So we have this little relationship. That's good to know. Now we can set up another equation involving CD and AD, because if we visualize it, these two triangles are not the only way that we can include CD and AD. We can also look at these two giant triangles, because you can see they're both sharing an altitude coming from point B. So let's do that. So I've already highlighted before, but I'll do it again. It's these two triangles. So let's write that one out as well. And in fact, because it's taking up so much space, I think we'll just refer to the one above here because it's pretty much the same. So we also know that triangle CBD, I think that's what it is, yes, CBD, and triangle ADB. Let's keep it consistent, ABD. Share an altitude from point B. So this means the ratio of their two areas is the same as CD over AD. Wow, there we go, like magic. The area of triangle CBD, okay, this one it's made up of 3 smaller areas, x, y, and 8. And AD is made over here. The area of triangle ABD is made up of these 2 areas, 5 plus 10. That's 15. If CD over AD is equal to x over 5, CD over AD is equal to x plus y plus 8 over 15. Guess what? We can set them equal to each other. And now we have our first equation. Something to keep in the back of our mind. So we're going to call that 1. So that's my tip to you. Always stay organized. Box things, number things, label your stuff. And I think I'm going to write out just in orange the thinking process of why we did this step, because I really want you to understand why we do things and why we go searching for things. So we did this because we asked ourselves, how am I going to relate CD and AD? This way we can get these 2. So that's why we did that step. Excellent. Let's continue. We go hunting for more triangles. So before we were looking at things kind of at this angle. So now it's time to change our perspective, maybe tilt our head, and let's look at these triangles. Because these 2 triangles share an altitude from point C. Let's drop it. So notice now, triangle ACF and triangle ECF share an altitude from C. This means the ratio of their areas. So I hope you can see we're just doing the same thing over and over again, just with different triangles. So it's very important to spot all of these triangles. So AF over EF, again, pretend like the C isn't even there. Area of triangle ACF is x plus 5. Area of triangle ECF is just y. Same process. If we need to get AF and relate it to EF, so that's these 2 sides. If we need to do that again, well then, maybe, just maybe, we can use these 2 triangles. Because those bases lie along this segment. So I hope you're really seeing the thinking process that I'm doing here. This time triangles ABF and EBF share an altitude from point B. This altitude would actually come down something like this. It's a little hard to draw it upside down, straight, but it would be like this. And of course, Both of these are obtuse triangles, so they get extended. Let's take some ratios. The area of triangle ABF is 10, and the area of triangle EBF is 8. And just for calculation purposes later, we can simplify that to 5 over 4. Again, the reason we did this, we need to relate AF and EF together. So now we have x plus 5 over y, and now we have a number, 5 over 4, so chances are very high we can find x and y if we combine it with this equation here. So let's write that out. We have another equation. We can set x plus 5 over y equal to 5 over 4. And this is never works. Anyways, this is number 2. So I trust that you can solve this on your own. You have equation number 1 over here. You have equation number 2 over here. So that's 2 equations and 2 variables, x and y. So you can just do the usual jazz, cross multiply them, move things around. I'm not going to go over that in this video because, again, we're more focused on setting it up instead of actually solving for the variables. But once you do that, you should get x equals 10 and y equals 12. So even though I didn't show that in this video, in the solution document that I'm going to attach, don't worry, I will write everything out clearly. I will solve everything, so don't worry about that. If you want to see a full solution, for the purpose of this video, we just want to go through these questions as fast as possible, as fast and efficiently as possible. And I'm not too concerned with solving. And if we remember our goal at the start, always ask yourself, you need to answer the question. The goal is not to find x and y individually. The goal is to find x plus y. X plus y ends up being 10 plus 12, which is 22. So therefore, if we answer the question, 22 sheep can graze in the north field. Great. So I'd say that was a bit of a more challenging question. So let's get on to question number 5. So I hope you can see just how important it is to get practice, because knowing the theory is not going to be good enough if you don't know how to apply, if you don't know how to train your eye to see the triangles and use what you know. Because if you just study the theory, you can study as much as you want, as long as you want, but you're not going to be able to solve these problems if you don't know how to use them. So that's why we're doing them. Because as you can see, they have to be used a little creatively sometimes. So here's your next question. This time we have a parallelogram, ABCD. Point X over here lies on AB such that XB is twice as long as AX. Let Y be the point of intersection of XC and BD, so these two meet at a point, Y. This time they're asking for what fraction is the area of triangle DCY, so that would be this one, to the area of the parallelogram. So basically, of the parallelogram, how much space is this triangle taking up? Okay, so to start off, I'm going to call this area number 1, the area of triangle CDY. Let's call this 2. We'll call this 3. And we'll call this little thing 4. So my strategy is to find maybe this area, and then what we can do is to compare it to the area of the parallelogram ABCD. I personally think it's just easier to find this area and then times it by 2, because recall BD is a diagonal, so that means this area is the area of the parallelogram is cut in half. So this left side area is equal to this right side area. So if we can just find the right side area and then multiply by 2, we have the area of the parallelogram ABCD. And I'm using this side, the right side, 1 and 2, because 4 has this kind of weird shape. So first things first, we use everything that we know. So this is where the prerequisites are going to come in handy, because we are going to go hunting for similar triangles. And we're going to be doing some angle chasing, because that's what we do for geometry problems and in math in general. Just throw everything you've got. Go hunting for some angles. So this is a parallelogram, which means these two sides are parallel and these two sides are parallel. Because these two sides are parallel lines means equal angles. We got a Z shape here, which means that this angle is equal to this angle. So I'm going to mark it with this little dash. Also, this angle, let's do 2 dashes, is equal to this angle. And that just comes from this Z shape. So if you don't know what I'm talking about, there will be videos on that at some point. Okay, so we have 2 angles that are the same. This means we have angle-angle similarity. Again, review similar triangles if you don't know what I'm talking about. So we found 2 similar triangles. Angle-angle, so that's AA. Similarity. And I'm talking about these 2. And remember, when we write out the similarity relationship for 2 triangles, we always need to stay organized with the order in which we write our letters. That's going to be very important. So we can get a few ratios from similar triangles. CD over XB equals CY over XY. Notice, CD, first 2 letters, over XB, first 2 letters, equals CY, letters 1 and 3, over XY, the first letter and third letter. So we always stay consistent with that. Now, we do not know any lengths, CD, XB, CY, XY, so I think it's time we go back. Actually, I should have done this at the start, but regardless, better late than never. Let's go back to our problem, and let's see if XB is twice the length of AX. Let's go ahead and call AX A, so that BX is twice as long. And keep in mind, because this is a parallelogram, AB is equal to CD. This means CD is equal to A plus 2A, so that's 3A. Since CD is 3A, XB is 2A. Now we can actually get 3 over 2 is equal to CY over XY. So it's always a great idea to label everything you know. We want to use all our knowledge. So that's the first step with these similar triangles. We can write something involving their side lengths, but another thing about similar triangles is you can compare their areas. So again, all of this is from similar triangles, so recall this useful fact about their areas. The area of triangle CDY over the area of triangle XBY is equal to 3/2 squared. This is a very, very handy relationship to know. We're going to be using it a lot. So that's equal to 9/4. And you might be asking, why is this true? Because this is quite a bold statement. And it's because if we have two similar triangles, so that one side is a certain so that one side is bigger than the other side by a certain factor. In this case, it would be 3a/2a, which is 3/2. So that's where the 3/2 comes from. And then remember, because it's areas, it would be equal to the square. I'm not going to go over that in too much detail because in my similar triangles video that I'm going to be making at some point, I'll go over this whole relationship. If this doesn't make sense to you, don't worry. I would recommend checking that video out, but I'll go over it and the proofs and applications, all that good stuff. Anyways, let's keep continuing. So from here, the area of triangle CDY is 9/4 times bigger than the area of triangle XBY, which kind of looks right to me, at least in this diagram, but of course you should never assume things are drawn to scale. So that's something to remember. And now, notice triangles XBY and triangles CBY. I hope you see it. They both share an altitude from point B. At this point, I'd say you should be pretty used to the visualization of the triangles, the altitudes, and the orientation, right? Like you should see it in your mind's eye. So I'm not really going to be drawing that out, but very quickly, it's just these two triangles, both sharing an altitude, dropping down from point B. If you ever struggle to see that, always just draw it out on your own. But I'm trying to save us some time here. This means that the area of triangle CBY to the area of triangle XBY is equal to CY over XY, which we know from here, which is why we did this before, is equal to 3/2. This means the area of triangle CBY is 3/2 times bigger than the area of triangle XBY. Number 2. So notice, I have written the area of triangle CDY in terms of the area of triangle XBY. I have written the area of triangle CBY in terms of triangle XBY. So we have this area and we have this area. That means this whole thing can be written in terms of triangle XBY, because this big area, triangle CDB, is equal to those two triangles, CDY and CBY. Let's substitute what we know. That will be 9 over 4 times xby plus 3 over 2 times xby. Which is equal to 15 over 4. Times the area of triangle XBY. And recall at the start what I said about the area of the parallelogram being equal to twice this area. And we found that area to be 15 over 4 times xby. So this ends up being 15 over 2 times the area of triangle XBY. Now, you may be wondering, why are we doing all of this? Like, we don't even know what the area of triangle XBY is. So like, what are we doing, right? Well, let's see. And this is something I want you to remember. Always keep in the back of your mind. If we go back to our question, because this is where the magic is going to come together, you'll be amazed. I think your mind's going to be blown. We want to find what fraction is the area of triangle DCY to the area of the parallelogram. We found the area of the parallelogram is here, and we found the area of triangle DCY. DCY, CDY, same thing, just read in a different way. So DCY, CDY, same thing, same triangle. We found that it is this. So if we notice, if we take the ratio of these two, we have something in terms of xby and we have another thing in terms of xby. So then those two are actually going to go away. So we want to find the fraction. So of the giant parallelogram ABCD, how much space does CDY take over? CDY is equal to 9 over 4 times xby. ABCD is 15 over 2. And this is a concept that you're going to be seeing pop up over and over again. When it asks you to find a ratio, they want you to find the ratio. You don't have to necessarily find out what triangle XBY is in the first place. And that's the beauty. I don't know what triangle XBY is, and I don't need to know what the area of triangle XBY is, because we just care about the ratio. 9 over 4 divided by 15 over 2 ends up being 3 over 10. So basically triangle CDY takes up 3/10 of the entire parallelogram. And I'd say that looks about right. Whew. I'd say that was the most tricky one we did so far. So can you see how the intensity is like ramping up? And do you also see how we're using everything we know? So we've learned about similar triangles to help us establish this relationship. We're using the same altitudes. We are doing good problem solving habits of labeling things. And then, of course, this last concept where we don't have to actually find individual areas. We can just find the ratio, because all we care about is how they are related to each other. And that's how we get a final answer of 3/10. Great. So yeah, that's a lot of things combined into one. Let's continue. Question 6. So question 6 says, the three sides of triangle ABC, so this one, are extended so that BD, so over here, this side is extended so that BD is half as long as AB. CE over here is half as long as BC, and AF is half as long as CA. And it asks us, so when we extend the sides, right, like this, we are going to get a bigger triangle here when we combine everything. So what is the ratio of the area of the big triangle DEF to the original triangle ABC? So notice how in this problem, I have drawn the diagram very, very big, and that's something I want you to do at home as well. I want you, for every geometry problem, I want you to draw a big bricking diagram. So that's what BFD stands for. You don't want a tiny diagram in the corner like this that doesn't really help and it could be hard to see. So always look at how much space I'm taking up. And now, let's get on with solving the problem. Notice we have our little guy over here who's reminding us with a friendly little tip that could help with this problem. It says to add a line. Which line? Some choices are better than others. So notice it's the exact same tip as question 4 from before. Because that is indeed what we need to do. We need to add a line. Well, actually 3 lines to be exact. That will help simplify this problem immensely. So that's the thing about problem solving. You're going to have to get lots of practice to know which lines you need to add. So don't feel too discouraged if you couldn't see these 3 lines, because I'm going to show you right now. These are our lines. So notice the concept of symmetry popping up once again. So we draw a line from a vertex of our original triangle to a vertex of the bigger triangle. Original to bigger, original to bigger. And notice that by doing this, we form a few triangles, such as this one. So we have 2 triangles which share an altitude from F. So we're getting a little feel of how we're going to use our same altitude principle, right? It's very important before you dive into a problem to have a method of attack, or like a basic framework of how you're going to solve this. Also, notice that this line over here has created these 2 triangles, one of them being the original triangle itself, triangle ABC, and triangle ABF, which both share an altitude from B when it comes down. So we can see we're probably heading on the right track. So by this point, I'd say we're getting pretty good, so I'm not going to draw out every triangle. That's up to you at home to tilt your head and have fun with it as well. But I'm going to just write it out. We have 2 triangles, triangle ABC and triangle ABF. Because they both share an altitude from point B. As always, I always encourage you, if you can't see it, just draw it out. So I'm talking about these 2. This means the area of triangle, ABF over the area of triangle ABC is equal to AF over AC. But notice that what we're given in the problem is that AF is half as long as CA, so then that means AF over CA is equal to 1 over 2. This means the area of triangle ABF is equal to half the area of triangle ABC. And you'll see why I'm writing it like this in a moment, because this is going to be a little more useful for the future. So after all that work, we can see it intuitively kind of makes sense. This is half the area of the original triangle. And now what we can do, remember from before I said there are two triangles which share an altitude from F. So notice how this same triangle is being involved again. So if we related this triangle to the original triangle, and now we're going to relate this triangle to this triangle, that means maybe we can get something that involves this triangle to our original triangle. Sorry, I'm drawing so many times. It's a bad habit of mine anyways. Let's do that. I feel like that was just very confusing, so sorry about that. I will try to reduce that in the future. Triangle ABF and triangle BFD share an altitude from F. This means that the ratio of their areas is equal to BD over AB. Notice that BD over AB from the start is once again 1 over 2. This means the area, let's be consistent, the area of triangle BFD is half the area of triangle AFB. But notice ABF, AFB, same thing. Notice now we can relate it to our original triangle, triangle ABC, because ABF is equal to half triangle ABC. That means the area of triangle BFD is equal to half of that, which is equal to 1/4. So we're getting some nice things. So compared to triangle ABC, this is half as big and this is 1/4 as big. And now it's going to be rinse and repeat. We're going to do the same thing again. So we've covered this side. Now we can look at this side. So I'm going to actually let you do this on your own. Don't worry, in the solution document I will actually write everything out fully. It's just right now I just want to get through this a little bit quicker, but I want you to repeat the same process. I want you to relate triangle BDC to the original triangle ABC. Then I want you to relate triangle, this weird triangle CDE, to triangle BDC. So once you relate this triangle to this triangle, and you relate this triangle to this triangle, then you can relate all three triangles with each other. Now, I'm going to tell you right now, you're actually going to get the exact same numbers. And that's why the symmetry in this problem is very nice. And it's the same thing when you do it one final time with triangle ABC, triangle ACE, and then this very, very weird one. Yes, triangle AEF. You're actually going to get the exact same numbers. So let me write that out. You're going to find that the area of triangle BDC ends up being half as large as triangle ABC. You're going to find that the area of triangle CDE is 1/4 of triangle ABC. You will also find that the area of triangle ACE is half as large as triangle ABC. And you will also find one final time, that is triangle AFE. Is 1/4 as large as triangle ABC. So notice we're relating all 6 triangles, 1, 2, 3, 4, 5, 6, to our original triangle, triangle ABC. This means triangle DEF, the big one, DEF is equal to the original triangle plus we have 3 copies of half ABC, and we have 3 copies of 1/4 ABC. Because recall, the area of triangle DEF is just the sum of all of these areas. So we have a half ABC, 1/4 ABC, half ABC, 1/4 ABC, half ABC, 1/4 ABC, so that's just 3 copies of each. That's where this comes from, and then if you treat ABC almost like a variable, you're basically adding up 3 halves, 3 quarters, and there's a 1, coefficient of 1 here. So that ends up being 13/4. This means, notice, without even finding the area of DEF or ABC, we can find their ratio to be equal to 13/4. And that is our final answer because that was what we were asked to find at the start. It says, what is the ratio of DEF to ABC? That's exactly what we found here. So basically we're saying that triangle DEF is roughly 13/4 times larger than triangle ABC, which I think, based on this diagram, that sounds right to me. Okay, so that's question 6. I really like this one. This was one of my favorites. And now question 7 is where things get a little bit more insane, but it is still solvable. So here we have a crazy diagram. So let's try to dissect it. We're given the area of triangle PUW for some real number x is equal to 4x plus 4. The area of triangle SUW is 2x plus 20. So that's this one, that's 2x plus 20. And it goes on, so on and so forth. So everything is just written in terms of x. So we are asked to find the area of triangle PTW. This one is closest to which of these following numbers? Notice that they're all pretty close to each other, so it would be pretty hard to guess this. We need to get this with surgical precision. So, we are not given much information, right, on side lengths. All we're given is a bunch of areas. So this means it's a very good candidate to use our same altitude principle. And by now, I hope you see the many triangles which share an altitude with each other. So these two I just highlighted, sharing an altitude from this point W that drops down. Let's get started. Triangles. QWV and SWV share an altitude from W. Again, I'm not going to actually draw everything out by this point. I'm not going to drop altitudes, rotate things, but I encourage you to make sure you really see that at home. If you have to draw it out yourself, go ahead and do it. So this means that we can compare their areas. We always do this because we want to compare areas with each other because we're given these areas. QWV, that's the same as QVW, is given in this problem to be 8x plus 50. SWV is the same as, yes, SVW, that's 5x plus 20. And this is equal to QV over SV. Now, we have one equation relating QV and SV, so let's go hunting for another triangle which uses QV and SV. There are a few candidates, but personally I'm thinking this one. This way we can just use these one areas. If we were to try and use this one, well then we would have to sum up 3 areas, and we don't even know this this area, right? PTW, that's the one we're trying to find. So that's probably not a good idea. But let's check. Do we know what these two areas are? So we have QVR and we have SVR. Yes, we do. So I think that's a great idea. So always try to look ahead, make sure you're going in the right direction. So triangles QRV and triangles SRV share an altitude from R. This means we can relate them to each other as follows. QVR is 8x plus 32. SRV or SVR is 5x plus 11. This is equal to QV over SV. And since these two are equal, now we can set these two equal to each other and solve for x. Because once we get x, then, well, we can rewrite all of these in terms of numbers. So if we set these equal to each other, I'm not going to show all of this work because I've actually done this to the side just to save time, but you're going to find that x equals 5. Of course, as I said before, in the full solution document, I will show every single step, so don't worry about that. This is just to save time for the video, x ends up being 5. So this is great, because if x is equal to 5, now we can just plug x equals 5 into all of these and actually fill in some numbers. So I've already done that to the side, and that was not the pencil. So I got these numbers: 24, 30, 45, 90, 72, 36, and that's it. We were only given 6 areas. Now I think would be a good time to add in a variable, since we don't know what triangle, the area of triangle PTW is. That's the one we're trying to find. Let's call that A, and let's call this B, since we're not given what it is as well. The thing is, now that we have numbers, all we need to do is find A and B. So if we're going to go searching for triangles which share an altitude, we're probably going to want to search for those involving A and B. And would you look at that, if you look at these two triangles, triangle PTW and TQW, they both share an altitude coming down from point P. And notice also that these two triangles share an altitude coming down from point S. So that's the general, that's our general strategy, our game plan. We're gonna go hunting for more triangles. So, triangle P WT and triangle QWT. Share an altitude from not point Q, sorry, from point W. Excellent. This means that the area of PWT to QWT, area of PWT is A, area of QWT is B. And this should be equal to PT over QT. So that gives us a big hint on how we should find our next triangle. We want to involve PT and QT, so we need to keep these lengths consistent. Those lengths are involved in these two triangles, as I said before. So that's why we are going to choose them. Just have to, I'm sorry if I'm scrolling back and forth a lot of times. I didn't actually do the rest of this problem off to the side, so we're doing it live now. Want to make sure I'm labeling this perfectly. PST and QST. Share an altitude from S. And oh my gosh, this is like, let's give it some space. Give it some breathing room. We can always compare these two from our same altitude principle. The area of triangle PST is the sum of these three areas. That ends up being A plus 54. QST is the sum of these three areas, so that's B plus 135. And this is equal to PT over QT. Again, if we pretend like we're canceling that s. This is great because now, guess what? We can set this equal to this. So let's do that. And this time I will show a bit of work. If we cross multiply everything, we are going to get some cool cancellation. That goes away, that goes away. And after some simplifying, we'll find that b is 5 over 2 times as large as a. Okay, so this is something to keep in the back of our mind. Because right now we only have one equation and two variables. Which means we need another, so again, even more, triangles involving A and B. Personally, I'm thinking, let's see. We can use this one, because this way we'll get, when we sum the areas, we'll get an A plus B, and then this one will just be a number. And we know that we're involving QV and SV, and we know that we have these two triangles as well, related by 90 and 45. So this would be twice as large. So that's the general strategy, so let's do it. So as you can see, it's the same thing applied many times over and over. It's going to work out like magic in the end. I hope I did not do this yet. So we're doing it live, I believe. QPV and SPV, yes, sharing altitude from point P. The area of triangle QPV, so that's QPV, is A plus B plus 90. That's all we can do for now. A plus B plus 90. The area of triangle SPV, SPV, is 24 plus 30 plus 45. I'm going to need to get a calculator for that. Or, let's see, let me do it in my head. 24 plus 30, 54, plus 45, 99. And this is equal to QV over SV, which we know QV over SV is equal to 90 over 45. So I sort of went a little fast there, so let me actually write that out again. This time triangles QWV and SWV. I know I'm going a little fast, so if you need to pause the video and actually, verify the triangles that I'm talking about, I encourage you to do so. So I think this problem is coming together. The area of triangle QWV, 90, SWV, 45. Which is 2, which is QV over SV. So that means I can put the 2 back in here. So if A plus B plus 90 over 99 is equal to 2, This means a plus b plus 90 is equal to 99 times 2 is 198. I think. Yes, 198. So then this means a plus b is equal to 108. Okay. Why does it always select the eraser? I'm going to box this. And I'm going to call this number 2. So now, all we're going to do is we have 2 variables and 2 equations, which means we can plug b equals 5 over 2a into this equation and solve it. But what we're going to find is in the end, a ends up being 31. So if a is 31, that means our final answer ends up being E. And then we have one final problem which I selected to emphasize the point that math does not lie, no matter how unbelievable it may seem. But anyways, I just want to give one final comment to this problem. Notice it didn't use anything that we didn't know. Share altitude, share altitude, share altitude, shared altitude, shared altitude, shared altitude. So it's the same thing 6 times, just applied in different ways because we have to look at all the different triangles, right? That's why I chose these problems, because they seem hard at first, but when you break them down, they are actually very, very simple. With that being said, as I said, let's get on to this one, the final problem of the night. From small to ginormous, that's what I've called this, because the final answer is going to surprise you. Or at least, hopefully it will, because it surprised me, certainly, when I first did this. So, it says, let R and S be points on the sides of BC and AC respectively, so R is on BC, S is on AC. Let P be the intersection of AR and BS, so when you draw these segments, they're going to meet at point P. Given that the area of triangle APS is 5, the area of triangle APB is 6, the area of triangle BPR is 7, find the total area of the big triangle. And maybe you can just guess why I'm calling it from small to ginormous, because you notice we got some pretty small numbers here, but the final answer is going to be, I can tell you right now, it's going to be big. It's going to seem unbelievable, but math doesn't lie. So let's check it out. So our first step, I did not put it as a tip here because you won't always be told this. This is just something that you're going to have to get through practice. Let's add a line. This way we make some triangles. You don't want to be stuck in that weird quadrilateral shape from before. So let's make our life easier and add some triangles so we can use what we know. So all of a sudden, because it's the last problem, I will be nicer and I will stop being so lazy. So let me go back to what I used to do before and actually draw things for you. So that it's easier to see. Okay, so triangles SPC. And did I erase the B? Yes, I did. BPC. Share an altitude from C. and I hope you can see that. If you cannot, I will add it in. So remember, BPC, the altitude is inside SPC. The altitude is outside because we're going to have to extend segment SP. And you know what? Let's call this X and let's call this Y. That way I don't have to keep calling it the area of triangle SPC and the area of triangle CRP. I can just call it X and Y. That was not this, my bad. And then I'm going to have to actually add this here. So that's X and that's Y. This means that we can relate these two areas which is SP over BP. So the area of triangle SPC we've called X. The area of triangle BPC is these two areas added up. Y plus 7. Hopefully I don't make any stupid mistakes, because if you can't tell, it's been a very long day recording this whole thing, so I am feeling very sleepy. I'm going to go to bed after this. Hopefully we don't mess this up. Let's see. We also have more triangles that share altitudes with each other. So this time we're going to focus on this side of the diagram. And why not? Since it's the last one, I'm going to stop being so lazy and tilt it for you. Fix these letters as well. My bad, that's not tilted as straight as it could be. There we go, maybe something like this. So, triangles. I believe that was P, right? Yes, it is. Triangles SPA and BPA share an altitude from A. Let's draw it in. So for both of these triangles, we're going to have to extend it out until it meets. This means we can relate these two areas like this. So notice we get SP over BP again. The area of SPA is 5 and the area of BPA is 6. So yes, notice the reason we're getting SP and BP again is because they are lying along this line. So now we can relate all of these to each other. Our first equation is, we can set them equal to each other. So our first equation is 5 over 6 equals X over Y plus 7. So I'd say that's the first useful thing to remember. And now it's time for us to change our perspective a bit and tilt our head, I would say, because this one equation is not good enough. We can't solve for x and y with only one equation when we have two unknowns, which means we need to get more equations. To get more equations, we need to find more triangles which share altitudes with each other. So let's tilt our head a bit and try to find something. So we originally divided along this line and looked at it as a left and a right side. But now, what if we divided it along this line and looked at it as this side and this side? I wonder how that would work out. Let's see. So I'm going to paste this again. And notice this time, you're going to have to tilt your head a bit. Triangles APC and RPC share an altitude from C. So this means that when we compare these two areas, APC to RPC, which is AP over RP, so we got these two segments. That is equal to the area of triangle APC is x plus 5, and the area of triangle RPC is y. Great. So if we could, and I'm actually going to copy this diagram so I don't have to add x and y manually every time. That was getting annoying. To relate AP and RP, maybe we can use the 6 and the 7. So I hope you see how I'm thinking. There's always a method to this so that things end up nicely. And why not? I know I'm not super consistent with it, but since I'm nice, let's actually tilt it this time, okay? So now, triangles APB and RPB share an altitude from point B. So this means if we were to compare them, area of triangle APB is 6, RPB 7. This is equal to AP over RP. Again, like magic. AP over RP, AP over RP. Time to set them equal to each other. So if 6 over 7 is equal to x plus 5 over y, this is equation number 2. I was almost about to solve it there, as you just saw, but I don't think I will. Of course, in the full solution document, I will do every single step, but for now, I'd say it's good enough. So, to leave it here, so we have 1 and 2 equations with two unknowns, x and y. So you're going to do the standard, cross multiply, and then use your favorite method to solving systems of linear equations, whether it's substitution, elimination, or some other fancy method that you like to use. But what you're going to get is you're going to end up getting x equals, believe it or not, this is all true, when you do the math, x equals 385, y equals 455. And since we need to find the area of triangle ABC, we need to add 5, 6, 7, 385, and 455. And when you do that, you are going to get a final answer of, believe it or not, 858. I know that sounds crazy, but this is the final answer. 858. So, from small numbers, such as 5, 6, and 7, in the end, you can get a big number of 858 for the total area of the triangle. And this is all true from the math, which can be verified. So math does not lie. And I would say this is a good problem to end with because we can leave on a positive note. These small numbers may be your skill right now, but very quickly you can develop into something big, right? You can get really good. So that's why I chose this as the final problem. You have homework. Unsurprisingly, as usual, you always have homework. So I have given 3 problems, just like last time. And here they are. In the full solution document, I will include solutions to all 3 problems. So as usual, 1 and 2 tend to be a little bit easier, although I will admit this time they are kind of hard, a bit harder. And then of course number 3, the one with the star, is, I'm going to admit this one is pretty hard. So I don't expect you to get that. I actually didn't get it myself either, I'm not even going to lie. But for the other 2, I think you can definitely have fun with that. So I don't want to give away too much, but I'm going to let you try this problem out on your own first, of course. But for number 1, if you need a big hint, you might want to add in this line. Sorry, that was horrible. A line from C to M for this problem. Again, going back to the concept of symmetry, you might want to draw something from the vertex to this point as well, and maybe that could help. And question 3, the only thing I can say is good luck, because it's pretty hard. So that concludes this same altitude principle. I hope you enjoyed, because we did a lot today. It was very, very challenging, I would say, some good geometry, but I'd say that's a good place to stop for tonight. So have fun with those 3 problems, and I'll see you in the next video. Goodbye.